Swayam Prabha. Digital India. Educated India.
Hello dear friends, welcome to this fifth lecture of Module 12 on engineering geological aspects of geothermal energy, coal bed methane, gas hydrate, shale gas, carbon capture, usage and storage. In previous lectures we have elaborated about CVM and shale gas. Now in these lectures we are going to stress about the geological aspect concerned to carbon capture, usage and storage. In this lecture, we are going to elaborate about engineering geological aspect, or in other words, geomechanical aspects of carbon capture, usage and storage. In these lectures, we are going to elaborate about introduction related to energy needs, use of fossil fuels, then carbon dioxide emission status on global level, then the steps for minimizing the carbon dioxide related problem, then CO2 geological storage and parameters for evaluation of storage site and trapping mechanism, geological formations and then implementation and constraint. Friends, as you know, the quality of life in terms of education, infant mortality and the life expectancy correlation with energy consumptions, and the global energy consumptions will increase dramatically in future in comparison to present due to advancement in society, and it will mainly depends on fossil fuels due to availability of reserves, their low cost and the investment in the current infrastructures, as well as still we are limited in development of the renewable energy resources for use. Currently 90% of total primary energy resources in the world are based on fossil fuel, and the use of fossil fuels is closely related to emission of CO2, carbon dioxide into the atmosphere. And as far as current concentration of CO2 is a concern in atmosphere is 385 ppm part per million, which is almost twice the concentration before the industrial revolution. It means the industrial revolution is one of the activity of the human race to increase the carbon dioxide gas concentration in our atmosphere. Anthropogenic CO2 global emission enhance about 7 GTC per year. This unit we are utilizing. And for example, only US releases 1.59 GTC per year and the China 1.78 as per data up to 2007. Other countries also emitted gases in terms of some GTC per year, and among the main resources as emitter for the CO2, the power plants account for approximately 40% of total CO2 emission. Once the CO2 released into atmosphere, the CO2 enters into the global carbon cycles and interact with the ocean and terrestrial sinks, and resulting a lot of changes at genetic level, at physical level, as well as chemical level. As example, the estimated net annual increase of CO2 concentration in atmosphere is problematic since CO2 is a greenhouse gas which are going to enhance the temperature of our atmosphere, and there are lot of complications in our nature due to increase in temperature like melting of glaciers, increase in level of oceans. Due to such type of disequilibrium resulting many type of complicated induced problem, the mean surface temperature has increased approximately 0.6 plus minus 0.2 degrees Celsius since the Industrial Revolution, and it may increase further at the approximately 3 degree 0 Celsius by the expected 2100 years in future due to present trend of anthropogenic CO2 emission in run of development and progress. The atmospheric concentration of CO2 as per threshold value should not exceed 450 ppm as per suggestion of UN Framework Convention on Climate Change. And thus a proper measure is mandatory to implement seriously. It is mandatory and serious need of the world to reduce such critically hazardous gas. If we are going to see one view here, CO2 emission as per person, we can see this trend related to our progress belonging to the underdeveloped country, developing country and advanced developed country regarding emission. As far as the observations related to global surface warming is a concern, we can see before here 2000 this measured temperature change from minus 0 to here 0 is enhanced due to higher concentration from 400 ppm to 600 ppm and expected in future at the 850 ppm with present trend of emission of CO2. As far as atmospheric, where the growth of this CO2 we are having 4.1 GTC per year, where the 1.4 GTC per year contributed by land due to land use pattern change, and due to 7.3, you can see here 7.3 from the fossil fuels contribution and 0.4 from the cement utilization. These major principal sources of the CO2 emission are increment causing in atmosphere. Among these 2.7 GTC per year is sinked in toward the land side and 2.3 GTC per year toward the ocean side. Due to sinking of this CO2 from atmosphere toward the land side and ocean side, resulting lot of ecological problems concerned to the species or component residing inside. So it is important to address such global problem which are going to create lot of disasters in future. So we have only two options. One, either we are going to suppress the use of carbon dioxide emitting fuels in terms of use of clean energy resources. So either going to minimize the use of carbon dioxide emitting sources of energy, either we are going to release the carbon dioxide concentration towards suitable host. So this second option, because this less use is related to some ethical understanding and some new alternative in form of renewable resources, green energy resources and others. However, the present status as well as future expected higher concentration of carbon dioxide requires proper capture, proper trapping and storage in suitable host. Number of hosts we have defined, and people have suggested regarding the disposal of CO2 in ocean, disposal of CO2 or storage of CO2 in land area, particularly saline aquifers and simple groundwater aquifers, some geological formations, etc. However, the common practice as suggested by many researchers to utilize ocean, but the storage of CO2 or trapping of CO2 and storage in ocean going to create lot of problem to the marine animals residing in ocean. That is a ecological problem and not suitable for survival of the species residing inside the ocean water due to enhanced acidity or reduction in salinity of water, which are going to suit for survival of the marine species. So we have different steps regarding the carbon dioxide capture, transport and the final sequestration of such hazardous gas generated from the fossil fuel use or fossil fuel based utilization from power plants. For this we have geological storage as a short term and long term suitable host. Because what is the benefit here? Because allowable injection technology, the geological host have large capacity and may give additional revenue by enhancing the hydrocarbon production if we are going to choose some hydrocarbon containing wells and basins. And what is the difficulty associated with CO2 geological storage? The major difficulty is concerned to economics, that is the cost. It needs additional energy consumption, approximately 20% for the carbon capture and storage, then monitoring, contaminations and liabilities. This method for storage of CO2 in geological host is costly and require lot of money expenses on different component concerned to storage of carbon dioxide in geological formation or strata. In ocean, it is in case of ocean, the major benefit is easy and relatively inexpensive. No porous media is required for storage of CO2. However, the difficulty is the transportation to the site from the power plant to the oceanic site, and one major problem is the hazards, water acidification and effect on aquatic life. That is the not authentic practice and opposite to the ethics of the ecological concern. Then another aspect is a permanent but slow chemical carbonation. The benefit, it is based on the thermodynamically activated process and it is thermodynamically stable in nature. So in future, breaking up the byproduct caused by the CO2 conversion is not problematic if we are going to practice chemical carbonation. And what is the difficulty concerned to this? So it is expensive and labor intensive. The major hazards related to trapping as well as storage of carbon dioxide is a change in composition of the lithostrata and porosity and permeability status and their impact on the groundwater. The groundwater is also our one of major requirement because the water is our lifeline. So the clean water is very important. So therefore the protection of groundwater is also our duty. Therefore preference of CO2 geological storage is a pertinent among these with a hope of permanent solution and stable and suitable. Chemical trapping mechanism include dissolution, CO2 and others, and the most trapping mechanism and safe disposal conditions are found and favored at the higher depth. Other method to mitigate global warming caused by the CO2 concentration induced increment in temperature and because of the natural climate fluctuations such as average glacial cycle period and others, lot of changes physically, chemically and genetically. If we are going to store carbon dioxide in geological condition, then there is some residential period in which the CO2 try to adjust within the disposed host and therefore the suggested minimum storage time for CO2 in geological storage zone range between 1000 to 10,000 years. The radioactive waste disposal repository also require minimum life of 10,000 years. And such type of structure for particularly disposal of CO2 in geological formation ranging 1000 to 10,000 years and nuclear waste also. So this problem is also a challenge in front of our geotechnical and engineering geological experts. Now we are going to see about CO2 geological storage and reservoir condition in which we are going to trap and dispose. Due to storage of CO2 in reservoir, there is a change in volume. Therefore, it is important to estimate the volume due to storage of CO2. The injected CO2 displaces the original fluid that fill the voids in geological formation. Original fluid, when we are going to inject CO2, then the already present fluids experience some pressure due to injection of CO2 and started moving from their inherent place toward the another place through the allowable spaces. The volume of geological formation bulk in term of bulk volume affected by injection of a volume of CO2. And the volume of CO2 is actually a function of the average porosity of reservoir N or phi. So we can calculate the V volume of bulk. Interest means the bulk volume as the volume of carbon dioxide injected in the geological formation divided by this porosity and along with some constant xi. So where the displacement coefficient xi is considered as 0.6 in medium with spatially correlated random porosity and can be very low less than 0.1 if the fingered inversion take place due to different activity like buoyancy effect, hydraulic boundary condition, and the use of multiple injection borehole. So the use of multiple injection bell bores can lower efficiency as much as the psi is approximately ranging from 0.2 to 0.1. For example, a target sequestration of the 4 GTC per year. So the total amount of CO2 to be sequestrated in the next 50 years is suppose 200 GTC per year or 730 GTC CO2 in a compressed state 0.7 ton per m cube, and this mud would occupy a bulk volume of 1050 kilometer cube. You see, the requirement of the volume of the geological strata for disposal of this amount of the CO2. The geological volume for storage would be bulk volume, and it requires approximately 27,500 kilometer cube for a porosity phi is ranging 0.2 and the displacement coefficient 0.5. Thus, a 100-meter thick reservoir would extend up to approximately 325 kilometer in each direction can be solved to dispose such amount of CO2. Now, another aspect is the carbon dioxide gas trapping, and the carbon dioxide gas trapping can be classified into categories. One is physical trapping, another is a chemical trapping. This trapping is principally based on trapping mechanism. As far as the physical mechanism of trapping, the physical mechanism of trapping includes structural and stratigraphic trapping by a cap rock requirement, by a hydrodynamic trapping by the slow aquifer currents, and capillary trapping by the interfacial forces. These components are important to facilitate the physical trapping mechanism, particularly in structural and stratigraphic traps, and we are generally utilizing a case of hydrocarbon trapment by nature. The chemical trapping mechanism is comprised of dissolution of CO2 in water or in mineral or mineralization, or CO2 adsorption on coal and rich organic cell, and CO2 hydrate formation. The most trapping mechanism and safe disposal condition are found and favored at higher depth. Besides these, there are natural accumulation of CO2 in Earth's upper crust, where CO2 has been contained by the geological time, and we have one good example, Ladbroke Grove and the Katnock gas field located in the southeastern Australia. As far as geological formation is concerned, for suitable trapping of carbon dioxide in geological formation, it is very important to select a situation which are having permeable and impermeable strata in alternation. And for such situation, we are identifying the stable sedimentary basin which are going to facilitate about CO2 storage properly, and if such basin is located nearby the power plant or source of CO2 emission. As far as the features of such basin is concerned, this basin should have a thick accumulation of permeable sediments zone overlying by highly impermeable seal or cap rock, and generally these permeable sediments we are having mainly sand, and they belonging to the sandstone, coarse sandstone, highly porous sandstone, highly permeable sandstone, and the seal or cap rock generally made up of shale or evaporitic minerals which are going to show a very less permeability, and the base should be impervious in nature so that not allowing any further movement. This type of situation we are generally encounter in case of hydrocarbon traps. So these basins are distributed widely in different countries, particularly in Australia, in USA, in Canada, in India, in China. Almost every country has some sedimentary basins except few, and the sedimentary basins fulfill the requirement for storage of carbon dioxide inside the surface. The permeable sediments arrangement capped by seal is going to provide maximum storage capacity of this reservoir zone and higher injectivity overlain by this. So this type of cap is not going to allow any movement of stored CO2 to the surface. As far as mechanism is concerned, when we are going to move from the surface toward the depth up to Z or any X, Y, any value, then there is increase in effective stress, and the increase in effective stress is going to reduce the porosity. Therefore, we are going to encounter low porosity and fine grained sediments with respect to depth, and due to this change in porosity and the grain size, in case of pores, the pore size depends on the porosity and specific surface, and in high specific surface, example is a Montemorillonite shale. Montemorillonite containing shale is containing number of clay minerals, and the mean pore size can be in the order of 10 to power -8 m, and this high pore fluid pressure at depth also lowers the mass density difference between water and CO2 and increases the solubility of CO2 in water and increases the absorption of CO2 if coal is present. Parameters of evaluation are parameters for evaluation of storage site. So the principal parameters for evaluation of storage site is mainly reservoir size and depth, hydrogeological features, geological features, geomechanical characteristics of the reservoir as well as seal cap or cap rock, then the surface temperature, geothermal gradient, tectonic stability, faulting and discontinuity intensity, then accessibility, then about the infrastructural facilities available in the area, and the proximity to the major CO2 emitting sources. Then the principal target for the CO2 and the distance between this principal target for CO2 injection and the CO2 emitting resources. The principal target for the CO2 injections are deep saline aquifer, depleted or semi-depleted hydrocarbon reservoirs, or unminable coal seams, or hydrate-bearing sediments. In hydrate-bearing sediments, a pilot test has been carried out in the Alaska North Slope. However, the deep saline aquifers are most abundant and could store 1110 to the 2700 GTC as per information given by Gale in 2004. So these parameters are going to influence the selection of storage site. One example here I have taken from this published paper, a pilot project conditions. The pilot project developed throughout the world, and at present there are more than 50 CO2 injection projects throughout the world, and the mean pressure temperature condition at these storage sites, you can see here the temperature variation and the pressure variation, in which in certain cases the CO2 in solid state, in CO2 in liquid state, in CO2 in gaseous state. Based on such phase type of patterns, we are going to utilize this concept for easy capture, transportation and disposal of CO2. Most projects involve supercritical CO2 and relatively small volume, compressed in nature at pressure and suitable temperature for the injection in suitable geological host. Next important aspect concerned to the carbon dioxide disposal, storage, capture and other aspects. We have some constraint regarding or during the implementation of the concept, and the injection of CO2 underground is implemented with technology generally as used in case of the hydrocarbon or oil gas production through conventional petroleum wells. And such type of techniques, Alberta has suggested the recovery of oil and gas through injection of CO2 in their conventional hydrocarbon test, going to get two hand benefit. One is going to use the CO2 as a injection medium, and another is getting higher and higher oil and gas. However, still the systematic geological storage of CO2 will require advances in risk evaluation, adequate evaluation of regional capacity and reservoir integrity. If there is any break in reservoir integrity, then there is a development of some major hazards related to natural hazards like earthquake and others, because the development of the change in porosity and permeability due to injection of CO2 is leading to formation of fractures, cracks and evolution of discontinuity that become site for the burst of energy, and the propagation of energy from subsurface toward the surface is going to create some earthquake. That is also a problematic. And this integrity, reservoir integrity is a very important. The matching emission source with sink and advanced monitoring techniques is required for the proper implementation of the disposal technology. In addition to this, the technical difficulties, economical, political and legal barriers have hindered the adaptation of carbon sequestration technology in practical field. Sometimes the people may fear lot of problems what the authorities are going to dispose. It may be nuclear waste, or it may be hazardous, or it may be a source of several virus and others. Therefore, lot of problems we are facing during disposal of CO2. Political, cultural, social, economicals and others. As far as technical aspect is concerned, the geochemical concept is mainly based on the property of CO2, and the combustion of fossil fuel yields CO2 among other byproduct. For example, burning of suppose methane CS4 plus 2O2 is producing CO2 and water. And the physical property of CO2 depends on the pressure temperature condition, and in turn into liquid at moderate pressure approximately 6.4 MPa at 298 K, and becomes supercritical when temperature is higher than 304.1 Kelvin and the pressure is greater than 7.38 MPa. Normally we are capturing carbon and disposing carbon for storage, or injecting carbon dioxide for storage in form of critical state. So these are some derivations may require further study based on different chemical relationship. Here we can see I have taken, there is a change in pressure linearly when we are going to inject the carbon dioxide. In case of offshore, you can see the change in temperature, and due to this CO2 sequestration, here there is a change in density from 0 to 500 in their traditional unit, and viscosity also change. This indicates the injection is going to change the pressure or stress condition, change the temperature condition, density and viscosity, where the density and viscosity are the parameters related to behavior of reservoir, and these parameters are surrounding effects. PT condition change, the wall compressibility typically in order of magnitude higher than that of water. In this complicated conditions, we are going to derive the fugibility and others following the Henry law and others. That requires more time to explain due to limited time, and we are going to make the system short. The reaction rate, here different type of interaction we are expecting after injection of CO2 in geological host. One type of interaction is the water, CO2 and mineral interaction. One is the water CO2 interaction and change in property. Then CO2 absorption on organic substances, and the coal and organic cells we are utilizing to see the unmineable coal mines are found most suitable, economical for injection of carbon dioxide gas, because the coal and organic cells absorb the CO2 suitably following the Lang-Moore-Sorpson's isotherms concept at different pressure condition. And then on another side we are getting released methane gas, which can be utilized as a fuel source. So two sides benefit. One, we are going to dispose the carbon dioxide or inject the carbon dioxide, On another hand, we are going to enhance the production of methane. Similar practice people are following in case of hydrocarbon field also. Due to change of the pressure, temperature and chemical characteristics, there is a lot of change in reservoir condition, resulting decrease and change in porosity, permeability, viscosity of the injected fluid and others. So the mixed fluid condition is mainly pressure dependent on the capillary action. So capillary pressure is following this rule, and the water CO2 interfacial tension decreases as the pressure increases due to injection and creating lot of changes following the capillary principle rule. You can read from anywhere or you can clear on online interaction. Breakthrough pressure is also one of important aspects which are going to create differences in mass density, convection and self-mixing, and facilitating convection and self-mixing. Then differences in viscosity, and the CO2 is going to lower the viscosity of the already present fluid like oil or water, etc. And the porous medium depends on the mean pore size. So overall business depends on the pore size, depends on the strength of reservoir and cap rocks, then the permeability status of reservoir and cap rocks following different geomechanical principles and law. Beside this, I try to attract your attention toward the changes incurred due to injection of carbon dioxide gas. Due to injection of carbon dioxide gas, there is a development of different type of discontinuities or modification in discontinuity or reduction in discontinuity. Such type of changes in discontinuity resulting change in porosity, permeability, as well as the compositional status of the reservoir strata as well as cap area. Therefore, the development of the new discontinuity sometimes resulting the mechanical waves, and that mechanical wave sometimes creates some vibrational effect nearby the project site and may create sometimes some hazardous evolution of discontinuity in form of fault and form of fracture and lineation and others. Friends, this interesting lecture is principally based on a paper, CO2 Geological Storage, a Geotechnical Implementation, published by S.P. Noja, D.N., Kim S.H., and the Santa Maria J.C. in 2001 in journal KSCE, Journal of Civil Engineering, volume 15, number 4 and pages 707. All the cross citation is present in this paper. You can, if you require, you can read by collecting this paper. This paper is very interesting and I have prepared this lecture through this. As far as conclusion is concerned, the fossil fuels account for more than 90% of the world total energy consumption, and the emission of CO2 to the atmosphere can causing warming and can be reduced by the development and implementation of carbon capture and storage technology, and the geological formation considered for CO2 storage mainly are here. People are utilizing saline aquifer, depleted and semi-depleted hydrocarbon reservoirs and unminable coal seams. The efficient short-term injection and the stable long-term geological storage of carbon dioxide are affected by complex hydrochemico-mechanical interaction that take place in the formation, including water acidification, mineral dissolution, and stress and volume changes. These water acidification, dissolution, stress, and volume changes sometimes created secondary problems concerned to stability of site. These hydrothermomechanical coupled process and emergent phenomena may hinder the storability and of injected carbon dioxide. Therefore, the technological development such as adequate tools for injection and reservoir monitoring are needed for the safe geostorage of CO2. Some advances in this direction is required for safe, stable, economical and environmentally sustainable disposal of carbon dioxide in geological formation. Dear friends, in this class we have elaborated about engineering geological aspect of carbon capture, usage and storage. The carbon capture is a very important aspect because the emission of carbon day by day going to create lot of problem due to increment in global temperature resulting glacier melt and other ecological, physical, chemical and genetic problems. Thank you very much.